Hello, this is Rick from MathX, and today we'll be doing number 22 from the AMC 10A of 2020. For how many positive integers n less than 1000 is the floor of 998 over n plus the floor of 999 over n plus the floor of 1000 over n not divisible by 3? Recall that the floor of x is the greatest integer less than or equal to x. Now, not gonna lie, just looking at this problem, it looks really scary. Like, we're not just dealing with one floor function here, we're dealing with multiple. And the entire question is just composed of floor functions. There's no nice term we can compare it to like in our previous floor function problems. So, I think we're gonna have to try something new, something different that we didn't do with that other floor function problem. Let's think about this. Let's try n out for a couple of cases and see what we get. So let's start from the very beginning. N is equal to 1. If n is equal to 1, we get 998 because 998 divided by 1 is 998, and the floor of that is just 998. Same thing can be said with 999 and 1000. So that's going to be the sum of each of this when n is equal to 1. And I know that this is a multiple of 3 because this is just 999 minus 1, and this is 999 plus 1. So in the end, we have three 999s minus a 1 plus a 1, which will just cancel out. So we get 3 times 999. And that's already divisible by 3. So this case doesn't work. How about if n is equal to 2? Then we get 998 divided by 2 is 499. 999 divided by 2 is 499.5, which the floor function of that is the greatest integer less than that, which is 499. And then 1000 divided by 2 is 500, and the floor function of that is 500. In this case, we have 3 400s and 499s and a plus 1. So we can see that the sum of these numbers is going to be 1 more than a multiple of 3, because we're going to have 3 499s and we're going to have 1 as a remainder. So this number is not divisible by 3. So let's see. Let's try n is equal to 3 one more, and then we can hopefully generate a pattern by then. So 998 is not a direct multiple of 3. It's actually 2 more than the closest multiple of 3, which is 996, and that's equal to 332. So 996 divided by 3 is 332, and since this is only 2 more than that, the floor of their division will still be 332. Um, 999 divided by 3 will give us 333, and it's just clean, just like that. So we know that this is 333. And then 1000 divided by 3 will give us 333.333, which the floor function dash just 333. In this set of numbers, we have 332 3 times, with each of these being 1 more than that. So the sum of this is going to be 2 mod 3, because it's going to go into 3 perfectly, but with these 2 extra ones left over. So we see that this case doesn't work. So what have we seen so far? Actually, no, wait, this case does work. I'm being dumb. This case does work, as it's not directly multiple of 3. So what have we seen so far? We've seen that numbers that are only divisible for a couple of them, but not all of them, work. As with 2. 2 was divisible with a couple of them, but not all of them. So then that set it apart, and we got 2 different numbers. Now, let's put on our thinking caps. If n is any number greater than 3, which we only need to care about because we've already tested the first three cases. If n is any number greater than 3, then if n goes into one of these numbers, it won't go into the other two because they would cycle in patterns greater than 3. For instance, let's say n was 5. Then n would go into 1000, but it won't go into any of the other two because it's the closest multiples to of 5 near 1000 are 5 less than 1000 or 5 greater than 1000. And since we're only dealing in a range of 3 consecutive numbers, it's not going to be exposed to that range. So then that automatically tells us that, let's say for instance 5 goes into 1000, the quotient we get here will be 1 greater than the quotient we get when dividing 999 by 5 or 998 by 5. So anything that goes into 1000 will be, when put into this function where we divide it from 1000 and take the floor of that, that'll give us a value that is 1 greater than if we do the same thing but with the 999 term and the 998 term. So if n is a factor of 1000, then the quotient we would get from the result we would get when dividing it from 1000, taking the floor function of that. Let's say if it was a, then if we do the same thing with 999 over n, we're going to get a minus 1. And if we do 998 over n, we're going to get a minus 1 again. And that's never a multiple of 3 because we're going to have 3 a's, but we're going to have a minus 2, which will make it not divisible by 3. Similarly, we can see that if n is a factor of 999, then let's say we'd get a result of a. 1000 over n would also be a because the smallest multiple of n less than 1000 would be 999. So it would divide by that and we would get a once again. But then 998, the smallest multiple of n would be significantly lower than 999. So we would get a minus 1 in that case. We don't need to care about the case where n is a factor of 998 because if n is a factor of 998, then if we take the floor of that, we're gonna get the same quotient or like the same result when we put it into this function every time. So if this is a, we're gonna get a, and that's still 3a, which is a multiple of 3. We're looking for things that are not divisible by 3. So we have to look for the cases where n is a factor of 1000 and n is a factor of 999. So then we're just hunting for all the factors of 1000 and 999. So we can easily find out the factors by this cool trick I know, in which we take the prime factorization of the number. So in the case of 1000, we get 2 cube times 5 cube, and then we add 1 to each of its exponents. So if we add 1 to 3, we're going to get 4 times 4. And then once we multiply that, we get the number of factors for the number. So we have 16 factors for 1000. And this trick works because essentially it runs through all the different powers of 2 that could go into 1000, which is in this case the range 2 to the power of 0 to 2 to the power of 3, which gives us 4 numbers. And then it matches those up with all the different powers of 5 that could go into 1000, which once again is 5 to the power of 0 to 5 to the power of 3, giving us another 4. And then it just multiplies the 2 because these are 2 independent counting events. If we use the same trick to find the number of factors in 999, we take the prime factorization again, which is 3 to the 3 times 37 to the 1. And then we add 1 to each of these to account for the 1s. So we get 4 times 2. So we get 24 different factors that we should hunt for when by adding these two up. However, there's one thing we need to take account in. So we already tested that. So let's say one of the factors is going to be 2 to the 0 times 5 to the 0, which is 1. And it's going to be counted twice in both cases. But that's not the only problem with this. We've tested 1, and when we add it up, it's going to be a multiple of 3, and that doesn't work for us. So we have to subtract the 1 from both of these cases. So we do minus 2. So our end result is 24 minus 2, which is 22. Now this problem is really it's really scary looking. And I literally shivered during the test when I first saw this. But if we wanted to attack it, we can't obviously formulate a solution on the spot. Because if we knew the solution to this problem, then why are we taking the test? We had to come up with a solution by looking for patterns in the numbers. And that's where experimentation comes in handy. This is a trick that you should always do if you don't know anything about the problem. If they give you a really nasty function like this, always try a couple numbers in there and try to generate a pattern out of that. Because if you just sit there thinking, you're not really getting anything done. So for these kinds of problem, experimentation is key.